not the screen. So, okay, so that quit. So now what I need is this. And notificaciones son desagregadas. And we need PowerPoint up. Okay, 8 y 9.
Porque el transistor está súper caliente. Lo desconecté.
I'll make it perfect game, quería.
Pues tanto ya porque le dices
All right, hi everybody. We've got 2 chapters to get through, and it'll take most of the lecture time to get through it. So we'll get started. We're going to look at ARP and at ICMP today. Very important. We have an exam in 2 weeks.
Yeah.
So I'll give you guys some stuff to kind of help prep for it, but we're not going to introduce a whole bunch of new material after today. Not maybe some, but not a bunch. Okay, so to start with the beginning, which is always a good place to start, let's talk a little bit about ARP. You guys have seen ARP before,
yeah.
And I think you guys talked about it in lab already this semester.
Yeah.
So the other students have told me some of the stuff that you guys picked up, so I will try to avoid it. Yes? You don't see it? It's off. That would do it. Hey, at least WebEx can see it. So for once, I actually got them, and then I forgot about us. Yeah. So we'll look at some of the things that are different, and we'll go into it in a little bit more depth as to what goes on. There's a couple of confusing things about this and about ICMP, and my goal is that they won't be confusing at all by the time we're finished. Okay, so we should be able to get out, hopefully, cross my fingers, hace chingadas, and changuitas a little bit early. All right, so we're going to take another look at how ARP hops across a network. So just to make sure everybody's got super clear in this, if we take a look at our quad that has IP and MAC addresses with source here and destination here, this is me, and this is me, and this is the destination, and this is the next hop, or the destination, if it's at the very end of the journey. So as I draw one possible path that a packet would take to get across the network, as I move along, the destination is always the logical address. The source is always my logical address. The MAC address is always my hardware port here. But this one, first, it's this, then it's this, and then this is the next hop, and then finally at the end, I end here. So because this logical address is not affiliated with 3 of the 4 of these, I need someone to help me figure out what these hardware addresses are. And the way I do it is I hand ARP the IP address of the next router, and it hands me back the MAC address. So that's basically what I'm using it for. These diagrams in this chapter of this textbook draw things a little more specifically. What they show is that all packets go through ARP. They just pass through there on their way into Ethernet. You can code it that way. It's a little redundant, but it makes logical sense enough. It's not hard to understand why somebody would want to do that, so you don't have to go back and forth. Yeah, where do you get it? From the routing table. So on each router and in your own PC, you have a list of network numbers and the route, the port you're supposed to leave on to go get it. So once you know the physical port that you're supposed to leave on, you activate ARP on that port, you have it broadcast out on that port, and everybody that needs to hear it should hear it, and hopefully including the device that has that IP address, and it will respond. and now you've made the binding. You'll cache that for a while, you'll hold on to it, so that you don't have to ask every single time. And for a PC, it's usually ridiculously redundant because there's usually only one place you can go, the router, the one and only router that you're connected to. But for the devices in the middle, it's sort of the opposite problem. You have lots of places you can go to, each of which have exactly one device at the other end of the cable, the next router. It's never a LAN with lots of devices. So you broadcast it out for exactly one device at the other end, which you probably already know the address of because you've watched it send at least one packet. If it doesn't send at least one packet, you'll never know it's there, and it won't be in your routing table, and you'll never send something down that port. So there's a bunch of kind of ironies wrapped around it a little bit, but that's how you get the next hop address is you give the IP routing module your IP address. It goes to the routing table, which is maintained by the routing software and updated every 30 seconds as needed, and it will tell you which port and the IP address of the next hop. So that's one of the things that confuses people actually about ARP, and so we'll show a little bit more detail in here. Okay, so ARP is always drawn in the bottom part of one of these diagrams to show you that it's actually kind of in between layers 2 and 3. Some people will actually call this like layer 2.5 or 2.9, or they'll make up some idea to help you understand it's not quite at the level of IP. And what this shows is IP passes its packet to ARP. ARP will insert the last hardware address, and it may hold on to it in order to figure out how to do that, or it may already know the hardware address. But either way, ARP is the one that has the answer. It either has it or it's going to go get it, but it's always ARP. So if you just pass all of your packets to your datagrams to ARP, it can fill in the missing blank and drop it on down to Ethernet. Okay, the ICMP chapter that comes next will cover this box in the corner, which is conversely shown at the top of the diagram, meaning it's a layer 3 protocol also, but it depends completely on IP. ARP can run under anything and on top of anything. It doesn't have to run underneath IP. It can run underneath any logical technology, and it can sit on top of any hardware technology. So we'll take a glance at a complicated example that's not just IP. So you ARP things out. One of the interesting things, if you start to kind of decipher what's going on inside of these packets, you have your Ethernet frame, and it's got its Ethernet header, and you also have your checksum at the end, the CRC code. And inside of that, you have your IP header and its entire payload. Wow, that's the most parallel I've ever drawn a line in the 20 years of teaching. And of course, I can't repeat it, right? So the very next one looks like crap again. And then after that, you'll have, oh, I thought I changed colors. After that, you'll have a transport layer technology, typically TCP, right? One of the two, but we'll just pick on TCP for now. So you have the header and the payload for that. And then at the very end, you'll have, what color shall we have? We'll have green. I like that. Let's do green. You'll have whatever the message is from the application. That's normally with Wireshark what you're going to see. And if you look in there, you'll see Ethernet first, then IP, then the transport layer protocol, and then it usually can figure out what you're doing with your message. It'll tell you it's encryption, or it's DHCP, or it's an HTTP page, etc. With ARP, this is not what you're going to see. With ARP, you're going to see something different. You will have Ethernet for our examples in this book because that's what we're going to run on top of. And you'll still have the Ethernet header, but then that's all you're going to recognize, because after that, it's an ARP header, and then this very specific data structure. It's not variable in length. Once you've told it the technologies it's working with, it's specific to the layer 2 and 3 technologies that it's running above and beneath, respectively. So it's not like you have a header, and then you have some options, and then you have a big, long variable length thing where you can fill it in with whatever you want. No, it's basically one small data structure. So it's not a big packet, but it has no IP, no transport, and no application message inside of it. So here's what it looks like. There's a place in there to tell it the hardware that you're working with and the length of an address in that hardware. So Ethernet is an example of a hardware, and it uses 6-byte hardware addresses, FA 6329, etc. And the next thing it wants to know is what the layer above it is. That's the protocol type. We will use IP usually, and the protocol length here is talking about how many bytes do you need for an address with this technology. And since it's IP, we need 4 bytes, 32-bit IP addresses. That's it. Then request or operation, and then there's 4 blanks, always these 4. You fill in the 3, just like we did up here. The only one that's a question, I want to switch colors so we can see this. The only one that's in question is this one. So you send this packet out through ARP. It will drop it out on the network for you. Someone will fill in this blank and send it back to you, because this is the hardware address that you're looking for that's associated with the next target IP address, or in our case, the next hop IP address. All right, so back to the diagram for a minute. There's all kinds of devices on the LAN. Normally, we are used to having confidence about whether a packet really has anything for us to be or not by looking no further than the Ethernet header. We can just look at the Ethernet header and we can see, does it have my hardware address, or is it a broadcast? But either way, we can be confident that there's something for us to do. It's a meaningful packet. Not so with ARP. In fact, the opposite is true. The vast majority of the time when you see an ARP packet, if you're on average just any random device on the network, the vast majority of the time it's not for you. And you will not know that by looking at the Ethernet address, because ARP sends everything out broadcast. So it'll send everything out. Every device on the LAN will pick it up and then do what? There's no IP in it. There's no transport. You're going to have to hand this packet up to your ARP software to figure out if it's for you. And what does it mean to be for you? It means that someone is trying to send something to you and they need your hardware address. So for what kind of device is that never true? I don't know of one. That's a scenario, having a packet that someone wants to send to you, for every type of device. Phones, tablets, watches, laptops, everything. So printers, every device has to have ARP implemented in it. No matter how strange it sounds, they all have to have ARP, or they cannot belong to the network. So you're going to have to pull this packet in. You're going to have to hand it up a layer to your ARP software, because you still don't know if it belongs to you. You're going to have to decipher this data structure. You're going to have to look in here at the target protocol address and see if it belongs to you. If this is your address, then you must respond to this ARP packet by filling in the hardware address, switching source with destination, because now what was the destination is now the source, and sending it back. So this is a vector of attack, because if you send out tons of ARP requests to various people, depending on the type of device, you can bog them down with it. You can slow them down considerably. So I'll show you an example from a Cisco device. It may come up if I'm lucky. Here we go, right here. So here's a Cisco device that is sending ARP requests out. And we could probably figure out more about exactly the type of device, but let's look at what one of these is. Here's the bit data. Here's my Ethernet frame. It knows it's going out to everybody on the network. Everyone's going to have to look at this packet. So you've just taxed everybody on the LAN. You've given everybody something to do. And here's who you are. The type in here is ARP instead of normally IP. And here's what's in the data structure. Here are the 4 blanks. I have 3 of them filled in. This one is empty. It's with all zeros. So this is what I need you to fill in if you are the person with this IP address. All right, got it? So that kind of matches what's going on. But why would a Cisco, I mean, Cisco doesn't make laptops. A laptop might want to know who people are. But why would a router send a message out destined for every IP address on the LAN that gets broadcast to everyone? It's an ARP storm. It's illegitimate. It doesn't take long to figure it out. There's 600, I think, in here, a little over, and 29 seconds. So about 20 a second are going out the door every 50 milliseconds. There's one headed out. And what Wireshark does for us is it always tries to give us a little summary, one line that we can kind of scroll through and look at quickly. And all it's telling us is there's an ARP packet in here that is trying to find the address, the hardware address for 226. And so it says, who has 226? Tell 216.1. Well, that's the person who's asking, 216.1. So this string doesn't exist in the ARP packet. This is just Wireshark's interpretation of this data to make it easier for us to read. But I like to dig down into it a little bit more. You can also see some other ones in here. Here's a ARP that I traced. And this is one from the Sheraton Ambassador Hotel downtown in Centro, in Monterrey. It's the crappiest hotel network I've ever seen in my, consistently bad in my life. It's never better, and people complain about it, and it's like the first thing you talk to people about at the bar. Because I used to be there every single week. So I have like this super platinum status with my own dedicated Marriott representative that talks to me on the phone and stuff like that. So I've talked to lots of people. You can guarantee business traveler shows up and you end up at the bar near them, which is tiny little bar, but it's nice, very nice bar. That's going to come up in the first 30 seconds. Hey, what have you tried? Have you tried the internet? So it's kind of funny. So here's a bunch of ARPs going out, but this time it looks more legitimate. Here's one coming from Cisco, Dell, a Microsoft phone, probably me. I think that's the end of my hardware address. And some of these other devices on here that could be point-of-sale stations or thermometers in the refrigerator. I mean, who knows what this stuff is? Here's a Chinese device that I don't know really who makes it, but you know, we could go look it up, given the real hardware address, etc. All right, back over to where we were. So you've got your preamble and your CRC, your Ethernet header. The type goes here. This is where you tell Ethernet it's an ARP packet, and then you've got your contents. And the size doesn't change coming and going. It can change on a per port basis because you may have a different technology plugged into every port on your router. You may not use Ethernet everywhere, and therefore they may not have the same length of hardware address. But on a router, the logical address is always going to be IP, and it's always going to be 6 bytes or 4 bytes. Okay, so 4 different scenarios, and this is a little hard to see, so I'll zoom in on it. You can need to send something to a device that's on the same LAN from you to someone else, and you can find what's on in your ARP list. You do accumulate entries in your ARP table, and you can look at them at any time. Here's what mine look like. We can make it grow if we want to, but maybe it'll grow on its own. The first day this week I tried it, I ended up with my loopback address in there, which is kind of interesting because I didn't expect that. But I wonder if I have Mailcatcher installed still. No, I need to go back and install it. Okay, so that would definitely cause my loopback address to show up. You can have a scenario where you're going to have to send it through a router. Salud, you're going to have to go from one router to the next. Or, of course, the last iteration is from a router to the destination. So you can write your code to look for situations where the hardware address belongs to the destination address. You can notice that the IP address that you're handing to ARP is the same one that's in your datagram that you've been holding on to this whole time waiting to get this answer back. So all this stuff we've talked about, all this happens while ARP is holding on to your IP datagram. So these IP datagrams get held onto a lot. First, the message at the top has to be delayed while TCP figures out how to break it up into segments. And then you have to wait for TCP to handshake. And then it can start sending the segments. And it starts with a window size of 1, so it's going to send a very little bit at a time. Your segment will be broken up into MSSs and et cetera. Then you get it down to IP, where you have processing delay there to look up the routing table. Now we've got ARP. All of this delays the transmission of your first packet. After that, things pick up quite a bit. You don't have to do half of that I just talked about, but it's surprising how quickly we can get a page to start loading, because all of this has to happen first. And like you'll see from a New York Times page, if you load something that's got lots of different objects parked at lots of different websites, then you'll be opening these connections and doing ARP for every one of the IP addresses. So what I'm going to do is pull up an inspector. If I can get it to run. There's some really cool inspector. There we go. Okay, so here's a little add-on to Google's Chrome browser that if I go to a place that causes HTTP message to be sent, it will collect them and display them for me live. So all of these are different sites, and unless they end in unless the host name is exactly the same, they'll each cause ARPs to happen. Now, it depends on your implementation. If you choose to just guess to send everything to your default gateway, if it's not in your ARP table, then you can do that. You can just get away with doing that. So a couple things I want to see. Hasn't changed my ARP table yet, so I am not ARPing for all of these things. The other thing I want to do is pull up Wireshark, start a trace, stop this from loading. Can't believe it's still not loaded. Stop. And let's watch what happens. Okay, so there's an ARP there. So I'm loading this page, and it's obvious that the way my system wrote the code, I was getting so good there, and then all of a sudden it just goes to hell, right? I was getting ready to brag on whoever wrote the code for this system. That's pilots tense radio messages show Boeing jet hit trouble right away. Well, that's not good. Okay, so I'm very curious about what all these are and why I keep asking for the same ones over and over and over. But what I'm basically showing is you can see ARPs there, and you can see HTTP messages here. But you're not going to see me because it's encrypted. And you can see TCP handshakes. They usually can't hide those. So I had to make 1, 2, 3, 4, 5, 6 different handshakes with 6 different IP addresses that all exist inside of this list of HTTPs. And they're all 200s for the most part. These are 302s. These are redirections. So these utilities are unbelievably helpful and didn't exist a year or two ago. It's just this part has gotten a lot easier. No, but this HTTP capture add-on to Chrome, that makes it super easy. What's ironic is I can't do trace routes or pings hardly anymore, but I can do this. So I guess we'll just wrap ourselves around what we can do. Okay, I don't know why I'm stuttering. I haven't done that in a while. All right, back over to where we were. Hopefully I'm filling in some holes in time, starting to tie things together. That's my job is to try to stitch these things together when we look at these protocols. It doesn't make any sense to just learn the protocol and walk away from it. I'll only cover it if we can relate it back to what we've got. Okay, so if we come over here to this example they've given us, I have one of these grids, IP, and MAC. And I also draw these grids for IP and port, which is the layer above, so you got to keep an eye on me when I do it. And they're asking us what's going to be filled in the data structure. And so we know the data structure looks like this. I will draw two of them. You'll see why in a minute. The source is .20. The destination is .25, it looks like here. And the source is :10, and this is I don't know. So the dot, let me see if I can keep from screwing this up. The .20 will go here. The .25 will go here. The :10 will go here, and this will be blank. It gets broadcast out to everybody on the LAN. On the way back, what are these four entries going to have? It won't be 10 and 20. Why not? Exactly. The source is now the destination. So this will be the AB that we filled in. This will be the 25, except I made it into a MAC address. 25. This will be a : what was it, 10? Yeah, it was a 10, and this was a .20. Okay, good. So they show you the example here, but that's exactly what we just went through, so we don't need to go through it again. You can have things called proxy ARPs, which is when you teach a device to answer on behalf of devices that cannot see your ARP request. Why would you want to do that? One example would be if you want to isolate two parts of a network that are actually in the same subnet and bridge traffic between them. So in that case, this request from the PC on the left will go no further than the router. The router can either forward it on as an ARP request, or it can just answer the request and say, just send it to me. If he does the first one, then he's going to have to keep a list of hardware addresses that he's supposed to pretend like he is. And he can do that. They can add multiple hardware addresses to your network card and say, pick up packets that match any of these, and it will. And that's a very useful thing to have, particularly with a network monitoring tool, a network sniffer. If you want to see what packets are going to a certain person, you can start grabbing them that way. Right? It's not a change it permanently to one. You can add more. Or the more common way is just to lie to people and tell them that the hardware address they need to get here is you. And it doesn't look like a next hop, it looks like the last hop. So you'll answer for it that way. You can run ARP on other technologies. You can run it on top of ATM. One of the things that ATM provides is this illusion of a dedicated virtual circuit, a private virtual circuit. So it's already got one layer of abstraction going on top of the hardware to create this set of what look to you and me like tunnels, but which are actually implemented in the switches along the way as really fast forwarding rules. So when a packet shows up, there's no looking up in the table, there's no making a decision, it's got a label, it's byte for, just as soon as you get a byte, it's forwarded out the next. So it acts like a real, legitimate, no congestion, never a drop packet, no collision, dedicated circuit network, which is why carriers loved it, because you could really implement successfully, totally successfully, circuit switch networks on the same data shared network that you're implementing IP. So that was very well engineered. It was a really cool design. And there's some maybe still out there, but I'm not aware of anybody that still uses it. So we use it to just show you sometimes these ARP packets get modified to fit certain types of technologies, not super important to us. We're not going to spend much time on this because we just don't care. Sorry. Okay, we're going to take a look at how we put together the software modules in this. So first of all, you have a cache table of the entries you've already learned, and you'll hold on to them. They expire after time, like every other cache we've looked at this semester. Like DNS, like routes, they get old and may need to be refreshed, hardware addresses and mappings for IP and all that kind of stuff. So this one just happens to hold the binding between IP and hardware addresses. The output module is here to get things out of here. Just remember it like that, get out of here. So leaving the device, going out onto the network. That's the output module's job. And like we talked about before, IP hands all of its datagrams to the output module. The output module will look to see if it already knows the hardware address. If it does, it will stamp it on there and send it out the door. It's done. If it doesn't know the hardware address, here's what happens. It will create a queue, if one does not already exist, for all packets that are going to be showing up for the next few seconds while you're waiting on to learn the hardware address you're trying to get to. And while this, you drop your packet in that queue first, and there could be some others. While that happens, you quickly send out an ARP request to learn the hardware address. Once you get it back in, it comes into the input module. You add it to your cache table, and you dump this queue of accumulated packets intended for that address as quickly as you can out through the output module. So these don't just come from one device necessarily. Depending on how you've got your IP addresses and things configured, you could have lots of people trying to send things to that hardware address. Different programs running on different ports and all kinds of stuff like that. But you have as many queues as you have people who you're waiting to hear an ARP reply from and are waiting to empty the buffer. So these are very transient in nature. You will try to get an ARP reply multiple times before you give up. So this can accumulate if the other end is not responding quickly. Okay, the input module is responsible for bringing things in. Yes, sir.
You don't have the target address, right? So you ask for it, you drop it,
Right.
So you expect the response from everything to that?
No, only the one who looks inside the ARP packet and sees that the IP address is one he's supposed to respond for.
Okay, so all others that see
Drop it. Yeah, but it's a denial of service vector. So let's say you are IP and I'm ARP, and you hand me a packet to go to him, but I don't know he's sitting at that table. So I tell you, hold on a second, and you're like, I don't do hold on a second. I don't do that. If you want to hold on a second, you hold on a second. I'm busy handling the next IP datagram. So you basically hand me the entire datagram and tell me it's your problem. Where am I going to put it? I got to create a queue and stick it there. And I turn my attention to try to figure out where he's seated. While I'm doing that, you continue to send me packets for him. And I'm like, hold on, I don't know where he is yet. I don't do hold on. I told you that. You need to hold on to these yourself. So I'm hoping that this doesn't take very long because the buffer is going to fill up. That's another attack vector, by the way. You can intentionally give things to IP addresses that are in the subnet that don't exist, and you'll force ARP to try and accumulate, and then you can try overwhelming ARP.
So like you record the different IP.
Yeah. Different IP datagrams. Each queue is for a different destination IP address. So let's back up a little bit and go into a little more detail. So how did you know the IP address that you wanted me to send this packet to? How did you know the IP address for which you're now asking me to get the hardware address? You're layer 3, you're the IP layer. It's the next hop. So what program is running inside all the devices across the network that's always trying to figure out how to get to things? Well, and the routing program is running. ARP table gets involved after the routing table has been built. So the routing table tells you where it is you need to try to connect. Where do you need to try to send it? Once you know that, then you're going to learn the hardware address using ARP. And you'll keep that information so you don't have to do it again. So the speed up comes the second packet. So back to our example. You have a packet that ultimately needs to get to him on the other side of the room, but I don't know that. All I know is that you're first trying to get to him because your routing table told you he's the next hop. So it's his IP address that you've handed to me. So I will go and get his hardware address for you, and then I will send the packet, the datagram for you. I don't give it back to you. I just finish building the Ethernet frame parameters and hand it off to layer 2. And then how he gets to the destination, I don't care. So since he's probably the one and only router on my LAN, every single packet you try to send for any ultimate destination, it's all going to go through him. So you're always going to get him as the next hop from your routing table, and it's probably always the default gateway. So you can write your code to kind of like, you know, you see the sun come up for 22,000 days in a row, pretty soon you see a pattern. Right? So that was a line, I think, from a movie. So I can also speed that up for you, but what it means is there's only one queue because everything you give me is going to the same IP address. It's all going to him. And so that makes it more of an attack vector. You could intentionally try to break your ARP by flooding ARP with tons of packets that are trying to get to an IP address that's on your LAN that you know is turned off. Yep. Oh, sure. You can have Wi-Fi and Ethernet or more than one router on a network like this, yes, but it depends on my association.
So then, like, you're responsible when you become QA, but it's because you always know that you're going to continue on the spot. With that same
Well, you need a queue because IP is dumping packets on you, and you don't always know immediately where to send them. So you have to buffer them. Make sense? So you're just throwing stuff at me as fast as you can. But by the time I learn where he is, I already may have accumulated some. Exactly. And after that, once I know it, it never gets past this output module. It never goes into a queue. And the cache table will expire, and this whole thing will start over again in 30 minutes. It's like a process queue, but it has packets. Yeah, exactly. It's exactly like that. Once you have a place in, you start pushing them out. So it's a last in a FIFO queue, first in, yes, first. I'm making sure it's the right one. Okay, so the code to implement this, the output module, is if you hand it something and it already knows the address, it's because it looked in the table and found that it had the state resolved. Resolved means I already know the answer, so you just send it. You get the hardware address from that entry in the table, you insert it into the argument field for your call, your function call to Ethernet, and then you hand it to Ethernet. You're done. You've now got everything Ethernet needs. If the state is pending, yeah. If the state is pending, then you've already had a packet in front of you that's caused you to go and send ARP out on the wire to try to get a response. So you've already done that. You've already broadcast your packet. You're just waiting on the answer. So you just get in line behind whoever was there before you in the queue. If it's not found at all, then you are going to be the packet that triggers the ARP. So you build a new queue, you drop this packet in there, and ARP gets busy trying to figure it out. That's it. That's what this module does. It counts the number of attempts, and it will give up pretty quickly if your site's not being responsive. If the network's the defense is to keep that number small, yeah. Or learn it. You can adjust it. TCP has a pretty sophisticated algorithm to constantly adjust window size or timeout values, and that's the one that's actually more interesting is how do you know what the timeout value is supposed to be, and that changes on a packet-by-packet basis. You could implement something that sort of keeps an eye on how long is it taking to get things back. You can look at how many milliseconds or nanoseconds it takes longest and assume that that's the device furthest away, or maybe it's the device that's slowest, and make sure you wait long enough for that guy to have a chance or two to answer your question. Yeah, but not too much. So that's the balance, right? If it's too much, then you're being attacked from the inside. The call is coming from inside the house. Do you remember those scary movies? Okay, the input module, you sleep until an ARP packet arrives. It could be a response to one that you sent, or it could be somebody asking you for your hardware address. If it's found in your cache table, then it means that this is an answer that's coming back. Because the only thing that goes into your cache table are other people's hardware addresses. So if you get a packet from an IP address, you look it up in your cache table, your ARP table, and you see that it has a state of pending, then it means this is the answer you've been waiting on. This packet contains ARP, and inside of it, you should expect to find the hardware address that will finish filling out this entry in your ARP table and will change this pending status to resolved. So that's what you're hoping for. DQ, and if it's pending, you will go ahead and DQ one packet and send the hardware address. You finish updating the table simultaneously and drain the rest of the thing. So your time is of the essence. You're trying to go fast. If it's not found and it is a reply, then create an entry into the table. If it's a request, then that's the last option. If the packet you just picked up off the network is coming from someone else trying to learn your hardware address, then answer them. Send them an answer. So this last part is what that ARP flood was trying to do, trying to get every device on the network to do this over and over and over and over and over, and hopefully slow them down. So it's,
Like if you said that I want to find out where it needs to go, it sent it to the hardware. It does not give it back to IP.
well, this isn't IP. This is all ARP code. So if we go back up to the box, once I send out, let me shrink it back down a little. Once I send out my ARP request, it's going to come back in here. I'm already moved on to the next packet also. I also don't hold on. I dumped it off in a queue. I sent the inquiry. I am not waiting around for the answer. I send the request out, broadcast it, and I immediately move on to the next IP packet. And maybe the next one, I already know the hardware address. I stamp it and I send it out the door. But at some point, what you're hoping for is their response to this ARP request arrives. And when it does, it will arrive here. So when it arrives here, if it is a response, a reply, then it's to a question that you asked. And therefore, there should be an entry in the cache table that is pending resolution. And you now have the answer. So what you'll do is you'll simultaneously hand it to this queue so he can start pushing stuff out while you update the cache table. Because time's of the essence. You got to go fast. If, on the other hand, the ARP packet that just arrived on the LAN and Ethernet saw that the type was ARP and he hands it to you and you look inside and see in the fourth field, that fifth field, that it's a request operation, then this is a question that you need to answer. It's not a response to anything you did. It's something that someone else wants. Someone's trying to send you something, and they need your hardware address. So you respond to it. You reply. For you. Only if it's for you. So you get it, and you make sure that the IP address is you. If you're a router, you may have a long list of IP addresses for whom you are responding. And if you're a proxy ARP, but for us, it's usually one. And if it is you, then you will switch the source and destination around. You will fill in your hardware address and send it back out as a reply here. All right? Exactly. You throw it in the trash. But it gets all the way up to here before you figure that out. So you've gotten deeper into the system. So it's, you know, just everything should end with, and so it's an attack vector. Right, so we can add that on to the end of every paragraph here. The cache control module we're going to look at in a little more detail. And I'll show you how that works. That one's actually kind of fun to deal with. All right, so here's a cache table, and I'm going to copy and paste it because we're going to mess with it. What happened to my... Well, it's a DOS, not necessarily a DDoS. DDoS is when the attack comes from lots of different people at the same time. It's distributed. That's where the first D and the double D comes from. If someone's hacked your code inside your PC and they're trying to overwhelm ARP by sending tons of packets that are pointing to an IP address that's never going to answer, then that's just a DOS attack, right? Or overwhelm the buffers and cause ARP to crash, and then cause layer 3 to crash, and then cause the system to reboot. Pretty good denial of service if the system's not booted up. Right? So that's one thing you can try. Okay, where did my layers go? Ventana, mi cuenta, ¿por qué tengo mi cuenta? Ventana, I don't know where it went. Sometimes it just disappears. I can't see it. Does anybody see it? Where are you hiding? Come out wherever you are. I don't want to quit because I drew some nice pictures today. Yeah, it's right here. But I don't know where it is. It's like, it's hiding. No, it's not this one. So what I'm going to do is just have to suck it up and quit and start it up again. Probably should stop Wireshark. It occurs to me that it's still running. Probably not. Yeah, I noticed this was 171,000 packets. Probably go ahead and stop. So we'll fix that without saving. All right, here you are, you little bugger. You were hiding behind the PowerPoint the whole time? Really? Okay. Now I don't need you because I have a blank slate to start with. So we're going to paste this in, and now we're going to make a couple of observations. First of all, not all these rows look the same. This is the only one that's free right now. There are several in pending states. So these are ones I'm waiting to hear back on, and the rest of these are resolved. So I'm keeping them in my cache for a while. So they walked through a couple of sample problems. The ARP module receives an IP datagram with the destination address of .89. So this comes from IP inside my own machine. This did not arrive over the network. This comes from the upper layer. It started probably at an application, but could be a handshake, who knows. So 89, is it in the table? Yes, it is. It's right here. Is it state resolved? Yes, it is. It's in queue number 8 in case I need it, but I don't because I have the hardware address. So I'll stamp it in there and send it out the door. Make sense? All right. Yeah, in case you've set up a queue for every one that's in here, just in case ARP is busy when one shows up and you have to enqueue it. It's also possible that, or guaranteed, that this one will revert back to pending at some point. Yes, yeah, for every destination address. You would normally not see this in a host because there's only one destination address they're always going to, and that's the router. Right? We're down at kind of layer 2. 20 seconds later, the ARP module receives a datagram destined for .22. It's not in the table, so I'm going to take my free one, and I'm going to mark it as pending. And, oh, that's not the free one. Today is brought to you by the letter F. Okay. Pending and resolved. So this one is ready to go. And this one is waiting. Pending, not ponding. We do a lot of that in Houston as well with all the rain.
But if it's ready to go, why is it waiting?
So that the next packet that shows up, I can just look up the hardware address without having to do another ARP all over again.
Oh.
So this is my cache. You notice there's a timeout column here. So this is where I do that timing. So far, since we started, there's 20 seconds have elapsed. I get one for 22, so I'm going to put it in here. Yes, it should. Thank you. I'm going to come up with some queue number. Who knows what it is? Doesn't matter. You can just pick whatever you want. I'm going to mark down that I've tried to send an ARP request, and I'm stuck. So, is it going to let me change slides? No, it's not there. It won't. Okay, and here it is. Pending, they gave it 23 was the queue number they gave it. So I'll copy that. That's fine. We can use 23 also. Okay, 20 seconds so far. Now continue at 15 seconds later. So we're up to 35 seconds, right? 20 and then 15. At this point, we receive a packet with a target of 71 from IP. 71 is in here, but it's pending. So this one is an input module, right? So the input module is where stuff comes in from outside, from the network. So this one is not coming from IP. This one is coming from the LAN. So this is an answer. So .71 was pending, and I learned that the hardware address is now something that ends in CA but starts with E3. I'll use E3 because this one also ends in CA. And I'll mark this as resolved, and I will get rid of the attempt, and I will start a timer for 900 seconds.
It always starts in 900 seconds.
By default. You can change it, but yeah, by default. If you're on a network that's changing a lot, then you may want to shorten that amount of time. But there's a balance there. Okay. And so that's what we see has happened here. 25 seconds later, an entire minute has elapsed. Yes, in this case, it was for us.
You have IP address from other.
All the time, if you're a proxy ARP.
Yeah, and you also have a hardware address.
Yes, but you don't need the hardware address if you have its IP address, because no one's going to care that the same hardware address is used on more than one IP. They won't care. So they'll just take you at your word. If you answer an ARP packet and fill in the blank, they believe you. So you can answer with your hardware address for 1,000 different IPs, and everybody will go, good, thank you, thank you, thank you, thank you, thank you, and they'll just fill in their table and move on. Right? So, yeah, they didn't really go into all that detail. They're just assuming, they're ignoring all the other ones that you receive. So what they're basically saying is, I went too far here. Come on. I hit the down arrow. Don't go twice on me now. What the hell is going on here? Oh, I did go too far. Yeah. It won't go further because it's the last slide. Okay, fine, be that way. All right, so I receive an ARP packet that belongs to me, and it has an answer to a question that I asked, giving me the hardware address for .71. That's what they should have said. They should have added more detail, a little more detail to it. So here's that final state of my table, and then a minute elapses. It's time for my cache control module to sweep through and subtract 60 seconds from the lifespan of everybody who's in my table. So this is going to get changed to 840. This will change to 390. This will change to 0. What should this change to? It's not 60 seconds old. It only showed up 25 seconds ago. So maybe we should just subtract 25 seconds from it.
Yeah.
So let's do that and make it 875 instead. And let's see what they do. That's what they agree with also. So this one becomes free. All this stuff goes away. And if it's an active destination, that'll be right back here again in a second. Literally. A second. Okay, make sense? So if I gave you one of these tables and threw some changes at you, I don't think it's that tough. You can kind of plow through it. It's actually kind of fun. Yeah, and it's also very easy for me to grade. Right? So win-win. Right? Okay, we're done with that chapter. about 15 minutes faster than the other two sections. What am I forgetting to tell you? Probably a story. Like, that's a big surprise. But man, it must have been a long one. You'd think I would remember it if it was 15 minutes long. I did have some hardware trouble, so maybe that's where I ate up some of the time on Tuesday. Well, no matter, we're done, and we talked about everything we need for ARP. There is an IPv6 version of ARP. It looks a little different. The addresses are a little bit bigger, but its idea is exactly the same. Okay, we're going to switch gears and talk about ICMP. And it looks like we may get out earlier than I thought. So ICMP is a control protocol that was added on immediately after TCP/IP when we realized we really didn't have a way to debug what was going on the network. So ICMP was developed, and it has two types of messages. One's where you can ask what's going on, and another one where a device will proactively complain when something bad is happening. So those are query messages and error reporting are the two categories of those. So we'll walk through that and some other odds and ends on ICMP. So we had no error reporting or error correcting mechanism in IP, so we needed to build this out. So now we're up at the top of the stack. Everything we do is going to ride on top of IP. So my ICMP protocol generates a string of bytes, a data structure, and it's going to fit inside the payload of an IP datagram. So far, that doesn't sound hard, but it's going to get a little confusing in a minute. So I just would kill to have that diagram back that I drew carefully at the beginning. So I'll just draw it again, but faster, probably better, I hope, the second time. So we have an Ethernet frame with a CRC. This looks like it's not going to fit much, so I'm probably going to run into trouble here. And inside of that, I'm going to have IP. So at least we got past having something weird happen there. So we have an IP header. And I'm going to not draw the other rectangle in here. I'll just leave it like this. And then what I'm going to have inside of this is ICMP. And ICMP, unlike ARP, is not just header. I have ICMP header, and then I have a payload that goes with it. So that's what they're trying to show you with this diagram over here. Okay, so what's confusing about this? Well, what's confusing is what's inside the payload. So what we do is try and, for error messages, give you back the offending packet. So think of it like a violent video game and an old medieval one where you catch an enemy and you chop off their head and you send it back. So I'm just, whatever it takes for you to remember, that's my goal here, okay? So whatever, hopefully, yeah. Well, literally, right? So, but hopefully you'll remember it. But you guys all play video games, so it's not like it can't be that sensitive of a topic. Everybody here kills a million things on video games probably. So the error messages that come back, they need to send me part of the payload. So if they chop the head off and send it back, why is that confusing? Because this is also the head of a packet right here. So I'm going to have two IP headers in the packet. So we'll walk through that to make sure nobody loses their mind on my watch. Okay, lots of different types and a couple of different categories. These types have sub-information called codes. So the type, once you've established that, there's a bunch of codes under it. There are a ton of types defined, like 100 at least. These are the ones that get used. And there may be one or two more an exception, but most of them have been deprecated, which is the IETF's word for saying it's fallen out of favor, you shouldn't use it anymore. People that write software to implement this now are no longer required to handle those other type codes. We've rolled them into other things. Where'd they go? Okay, so we'll walk through each of these, some a little faster than others. All right, so ICMP always reports the error message to the original source. So if a packet gets dropped on the 5th hop along the way, it's not going to complain to the router before, it's going to complain to the source to let them know what's going on. The error reporting is where the decapitation occurs. There's 5 different categories of error reports. You can never generate an ICMP because of an ICMP error. So you can have error messages cause error messages, or you can end up in a death spiral. You will also not generate an ICMP packet for any part of a fragment except the first piece, the one that has the original header and options in it. So if something's gone wrong, you can send back an ICMP error message, and the head that you will take is the IP header, which is on every single fragment. You will take the one that's on the very first fragment, and you will send it back. Okay? And you also will not generate ICMP ever for multicast packets, which keeps the internet from collapsing from sort of flame wars. And you also won't ever send one back for a special address, like your loopback address. Why complain to yourself? It doesn't do any good. You never listen to you. Okay? Am I right? Okay, so let's go through these a little bit at a time. So this is the way they chose to draw it. I prefer to kind of draw it a little differently. So inside my payload here, where is my eraser? Where is my eraser? My eraser is right here. There we go. It looks like an eraser. Okay. So I'm going to see if I can pull this off and impress you guys, a tough audience here. Payload. So what's inside this payload? It's time for orange. Inside this payload is the IP header of the bad packet. So I'm going to say bad IP header plus bad payload, but only the first 8 bytes. That's enough to figure out if it's TCP or UDP and port numbers, for example. So that may be of interest to you. So the easiest way to see this is in Wireshark, and we can make it happen. In fact, I can generate ICMP error messages at will by sending a trace route. Yeah, so pings usually won't, it's very easy to send one, but it's hard to get it past your own ping software. If you try to send a ping with like 100,000 bytes, it won't ever make it out the door, so there's no one to send you back an ICMP. But if you send one that's maybe 6,000 bytes or 5,000 bytes, then somebody may try to process it, and somebody down the pike may complain, and bingo, you have your ICMP error message. So let's pull this up, and I'll show you one guaranteed way of doing this. Damn it. Okay, stop. So what I want to do is generate some ICMP errors. So I'm going to pull up my terminal, and I'm going to ping. I don't want to ping. I want to trace route. I type 100 words a minute. 50 of them are backspaces. Oh my God, am I having a stroke? Like, what's going on here? All right. That's amazing. Yesterday, this was agave. The day before that, it was something inside our IT data center. Today, it's Escuela de Vanidades. Why? Okay, so what's going on here? It's as good a time as any to go back and take a closer look at traceroute, because now we're going to figure out what's really going on with traceroute. So I found how many hops between me and eTESM's website. So the 5th one is the website. So it took me 4 routers, 4 hops, 5 to land, 5 hops, however you want to define it, just, but you're reading it right. All right, so what are all these ICMP packets that are here? These are complaints. These are the time to live messages. If you remember the way we do traceroute, you first intentionally send a packet out on the network. It can be any packet at all, and you give it a time to live of 1, so that it will die when it hits the first router. And the first router will drop it, send back a complaint, chop off the head, and include it. So let's look inside this very first packet, which is coming from 104.1, and in fact, that is the first hop, 104.1. So let's look inside and see what's going on with ICMP and with IP. Well, the first thing is it's got a time to live of 255. Well, wait a minute, I thought it was supposed to be 1. Well, this is the response. This is the packet coming back from the router. It doesn't need a time to live of 1. It's just a regular packet. So it'll give it whatever time to live it wants. So that's not good enough. It's an ICMP protocol. And if I dig down in here, here is the part of my diagram that's in this teal, blue, and orange. We now begin to look at it right here. So the error type is 11, code is 0. That means time to live exceeded in transit. It has a good checksum. And what else is in here? A header and a payload. Here's the header, here's the payload. So if I look at the header, the packet that I sent it originally came from me, and it was going to 70 because that's the IP address of the website I was trying to reach. So when I sent the packet out, it was trying to go to 70, but I only gave it a time to live of 1. That's what caused the problem. And if I look down further in here, I was sending a UDP packet from this port to this port. We'll come back to the ports in a minute. Yes?
For the first IP header, like the one that's outside of the ICMP,
Yep.
that one did reach the next hop.
Which was me. So I can draw you the network that we're looking at.
For why don't you have an IP address like related?
Okay, so the router has its own IP address. He is sending me a packet. So the header on that packet has to be from him to me. There's no other choice. So why is he sending me a packet? Because I've sent him something that he had to drop. I've created an error inside the router. The error that I created was I sent him a packet that didn't have any time left to live. So I sent him this thing that died on my front lawn. I had a neighbor that gave me a cat once that like died that day. I'm like, so you just didn't want to deal with your cat dying? Is that pretty much? Thank you very little. All right. So they sent me back a packet. What's inside the packet? What's inside the packet is the IP datagram that I first sent him that caused the problem. So this turns out to be the problem IP packet. The problem IP packet has a bad header, and it has a bad payload. Because it caused an error in the router. This is, sometimes packets show up and they just have bad luck. They can just be the packet that just happened to fill the buffer and drop the packet. That's also an error that a router will complain about. But in this case, it really is this packet's fault because he sent me this packet without enough time to live. So I think I'm doing him a favor by complaining because normally when this happens, it's because there's a loop in your routing and you're sending a packet around and around and around, and at some point it gets down to 0 and you need to tell the source. But I did it on purpose this time. So I sent him the bad header and packet. He will take this, stick it inside a payload, and put it inside of his own IP datagram. So this IP datagram, inside the IP datagram payload is ICMP and this stuff. Yeah. Should be you. That's a really good question. There's probably some circumstances I could think of if I thought for a minute where it comes back and it's not you. One example I can think of is if you divert traffic, destination traffic to a site as it comes in, but you don't on the way out. A load balancer would do that. So packets that come in get distributed out to whomever is available. But when packets go out, you leave them alone and just let them go straight out the door. So the IP address that sent that packet, when it tries to come back, the load balancer will just hand it to someone. Randomly, it might be the same person. Probably they won't ever let you send something to that person in the first place, especially since this is UDP and there's no connection. There was no handshake with this. So these messages rarely ever get inside anyone's LAN anyway, ever, anywhere on Earth. They almost never make it into the LAN. So the network monitor sitting at the edge of the network is usually managed by the one and only group of people that could ever interpret it and care about it and do something about it anyway. So if they start accumulating lots of ICMP error messages, then that's something they want to know. Sending it to the person who generated the packet is probably pointless because the average person would have no idea what to do with it. Okay, so I had 104.1 in here, and I looked inside and I saw the ICMP datagram. But I have 3 packets coming from 104.1. Why do I have 3 packets coming back? Because I sent him 3 packets. So now what we have to do, and this is going to get hard because there's all this WebEx crap in here too, is I'm going to kill the filter, and we're going to hopefully let this, okay, good, they're next to each other. So we got super lucky. So here's the first pair. I sent a packet to .70, the web server, and I immediately got back an ICMP error message. So if I look in here, oh, my time to live is 1. This is what gets duplicated. This whole thing is what gets duplicated in the ICMP response back to me. It's right here. They handed it back, just so I'd know what it was. All right? And then here's where I sent a second packet to the same address that also had a time to live of 1. And then a third one that I sent with a time to live of 1. So I do it 3 times and I average the time. This is what it was like yesterday. The first router is just all over the map on response times. Less than a millisecond, 20 milliseconds. It's got issues. This is why our network experience sucks sometimes. This is a bad sign.
How could that be so? But no, but why? Yeah, that can. Why that
It's saturated. It's overwhelmed. It's dumping things out of its buffer. It's needs it to be rebooted. It's got too much other stuff going on. It's not, you have to look deeper to know what's going on, but it should never look like that. And it's that box right there. So it's probably actually the IP address of the master controller for all of these access point nodes, because they're probably programmed as a mesh, because they all have the same SSID. Okay? So one way to know for sure is to keep your laptop and walk into the next room with another hotspot and see if you can spot the hardware address of the device in the frame part, and if you keep the same IP address. If you keep the same IP address, it's a sign that it's a mesh instead, in which case all of these devices are all banging away at this one router port somewhere, and who knows how many of them are doing it. But when your packets leave and they start off with this, they can never recover. It's just all over the. This is why packets get out of order. You send one and it goes in a millisecond. You send the next one, it takes 10. That could cause issues. Okay, so 3 to there. Now the next hop was .69, right? So there should be 3 more of these down here going to .69. Well, I'm not going to see .69 ever because I never sent anything to .69. The point of the trace route was to discover that there is a .69. So the way I did that was still, I sent something to .70, but this time with the time to live equal to 2 instead of 1. So what we need to find are time to lives to 2. Here's one right here. This one also has a time to live of 2, and this one has 2. The next 3 should be 3s. This one has time to live of 3. You can see right down here. 3 and 3. That's me. 226 is me. That's my IP address. And then the last one is 4 4, and 4. Does the host care what the time to live is? The destination host? Once he receives the packet, does he care that it can't go any further? No, he doesn't care at all. So, and yet, here he is in my trace route. And also, if I look, here's one with time to live of 5. 1, 2, 3, that's this guy. He can't possibly be complaining about the time to live. And we have a hint that something different is going on anyway because Wireshark didn't color this red this time. The rest of them were colored red because I got an ICMP error message back associated with these that it has some filter that says that type of error is red. But these are unchanged.
Why do you implement one by one?
To discover one router and then the next one and then the next one. So what happens, what's happening is I have my device here. Whoops. Let me get back to my pen. I have my device here.
That's to calculate how many routers between you and
It's to discover. It's to discover.
How many hops there are.
So the first time I'm sending something all the way to here, to this point here. It's got this guy's address in it. But I have a time to live of 1, so it never makes it past here. And it sends me an error message back. Do that 3 times. The next 3 packets I send have a time to live of 2. They make it this far, but they're still addressed to the end because I have no idea how many routers there are. I'm going to keep doing this until I reach the destination. And then, so this one sends back an error message each time. And I do it again. I increment my time to live counter, and I continue this on until I finally get a response back from .70, and then I stop. Make sense? I wish the book would use this diagram. I think it's easier to understand. Okay, probably could have used the line tool on this. A little late. Yeah, you know.
That's why there's concerns about drawing.
Yeah. Well, they're good enough.
Yeah.
Part of the problem is the tablet is it lags. It's very slow. My handwriting does not look like this at all, but it does on this tablet. It can't keep up with me. So the next step up is like 5 times the cost, and I'm like, yeah, okay, we're going to stick with this.
Yeah.
Because I break them and lose them is the problem. Okay, so back to the question then. These guys sent back time exceeded error messages, which is the name of the ICMP error when your TTL goes to 0. But this guy can't. He doesn't care. You guys told me that he doesn't care. So how did we get him to send us an ICMP error message? We must have done something else that caused an error. So what's the second thing that we can put in every one of these packets that no matter whether it lands on a router or a host, because we don't know which one it's going to land on, that it will cause an error and send it back. So one of the things is the TTL too small. So that'll cause the routers to send it back. What do we do that causes the host to send it back? Send a arbitrarily large port number on which there is nothing listening probably. So if I go back and look at the port numbers I'm using, the first port number I was trying to reach with this was 33435. Then I go down a little bit further to the 2s, 33438, 33440. I'm just counting up. 33442, 3, 4, and so forth. So I use a really hard port number. So the error message that I get back is not going to be time to live. Now I can search, filter on ICMP again. What I'm going to get at the end is destination unreachable, port unreachable. That's how I know I reached the host. And it comes back from his IP address. That's how I know to stop. Until that happens, I keep sending out more packets. Now, Lots of routers along the way have gotten smart, and they immediately drop these things because they recognize it as part of a trace route. So what they can't do is ignore time to live exceeded. They must generate an error message, but they will not generate it. Most routers will not generate it when you send them a packet that is obviously built for the sole purpose of causing this to happen. And the way they tell is they see a port number in this range, they see that it's UDP, they see it has no payload in it. There's some telltale signs. So they don't have time to do that. Yeah, they won't do that. That's too much work. But security equipment can and will. And they can also see that you're port scanning because this sort of qualifies as that. So what Windows in the lab will do is their version of traceroute will never send a UDP packet. They'll just pick some other random type of protocol, Skype or HTTP or SMTP or FTP or anything else. They'll make up some well-known port number, lie their butt off and use it and send it out. And the routers are like, I guess I got to handle this one. And you trick them into sending it back. So if you use Wireshark in the lab to try to find these ICMP or the UDP outbound messages, you won't see them, probably. That took me a whole lab to figure out what in the hell was going on. I'm like, it can't work. I'm seeing the ICMP error messages. Why do I not? Yeah, and they let you change it to anything you want. In fact, mine will too. So they can't ignore them. You can coax them into telling you who they are. You can pick at them long enough, you can get them mad, and they will send you something back, tell you to knock it off.
I cannot change you like the bill. Okay, then I'll buy something with one, like that's worth one bill. Yeah.
Yeah, it's also like a movie Cool Hand Luke with Jack Nicholson at the beginning of his career when he shows up at a restaurant. I think he rode in on a motorcycle, and he wanted toast, and they didn't have toast. And he argues with them for a little while, and he's not somebody I would want to argue with because he scares me. And so he finally ordered a tuna fish sandwich on toast, hold the tuna fish. And the waitress was not amused. She also scared me. All right, so we made it through that. That's what's going on with the IP header. Here's the types and the codes. Type is 3 for destination unreachable. Believe it or not, this gets used for a whole variety of things. The host is down. The port number doesn't have anybody listening on it. It doesn't exist. The port number has been attached to a socket, but the program's not responding. I know the network number you're asking for, but I've lost my path to get there. I don't currently have a way to get there. Or I've never heard of this network number. I have no route. I have no way to reach it for you. So all of those things get bundled up into here. And so here are those different codes, and some of them anyway. This is also used for fragmentation. So if you arrive at a node on the network where the MTU is smaller and the router wants to fragment your packet, but you have the do not fragment bit set, it has no choice but to drop it and complain. So it'll send you back an error message. Some of the other things we looked at before, like source routing and stuff, if it can't do it, it'll send an error message back to you. Okay, source quench. This is something they never ever cover in the beginning networking class. This is a packet that a router sends back to tell you, I'm having to drop your packet because my buffer's full. So what you hope happens is if a router is having to drop packets, it's probably getting packets from lots of different places at the same time, and telling you to slow down isn't going to help anything. It's still going to be overwhelmed. So you hope that a variety of packets are getting dropped and enough people are being told that they're reducing their window size down to 1, that they all back off and it relieves the congestion. If it doesn't, then it'll collapse. So that's what you're hoping. It also sets a flag that gets sent along with the rest of the datagram to tell the person at the other end to complain at the transport layer. So what's going on? So this is a layer 3 complaint Where you really need to get the complaint is up to layer 4. So it can do that as well. Time exceeded message is the one that we just looked at. It's used for a second thing as well, fragments again. If you have a bunch of fragments at a host and you're trying to reassemble them and it takes too long and your timer goes off, you will complain with this. So this is one of the few types of messages that can be sent back either from a router or a host. Most of the rest are sent by one or the other, but not both. Okay? So like time to live messages, only by routers. Source quench, only by routers. Unable to fragment, only by routers, for example. Port unreachable, only by hosts. Okay. Type 12 is a parameter problem. This is dependent on how good you are at catching errors. So if you're running a version of code, or people want to find out if you're running a version of code that has a published fault flaw that will not respond properly to a malformed particular parameter, then you can try sending it to every router you can find and see if you can find one of them whose owner has not patched their code and infiltrate it. Okay, the next diagram is a surprise to a lot of people because they've never heard of it before. I think I've name dropped it earlier, and it's a concept of redirection. Couple of new things for a lot of people here. First of all, your laptop has a routing table as well. Every device does, including your phones and your tablets, and they have the full IP stack to even Arduinos and things like that. So you generate a list of. Of course they do. If you install Linux on them, they do. Absolutely.
Arduinos can have Linux.
Are you kidding?
I mean, Raspberry Pi, I know that Raspberry Pi.
And tiny Duinos and Arduinos and Beagle boards and all of it.
Yeah.
You bet. Yep. Full blown Linux. Yep. And you Bluetooth in your keyboard or you USB it in, and yeah, you bet. You can do all kinds of crazy stuff. In fact, the hack that brought down Dyn, the big IP provider, a couple of Novembers ago, and Telmex lost its DNS feeder that kept things updated, was attacked by 100,000 infiltrated Internet of Things devices, 100,000 Arduinos, basically. That they programmed to wake up at a certain time and start sending DNS requests to Dyn. And that's a tiny, tiny number to have attack you and collapse. It's usually millions of devices. It took a mere 150,000, 125 to bring Dyn down. So they probably lost business and should have. That stuff's, well, it's unforgivable.
Yeah.
The average lifespan of a CIO is like 15 to 18 months. That's because most of them are stupid. And they're not IT experts. They can't be. How could they possibly? You hope they're good managers and good advocates, and they surround themselves with people that are, as the network guys, people that the network guys would not call stupid. But most network guys I've dealt with, they think the CIOs are stupid, and the CIOs think they need to bathe more often and comb their hair once in a while, and so it goes both ways. There's no love lost. But that's half the fun, frankly, when you're in a technical job, is to pick on the suits, they call them. Okay. All right. So host, and no bad intentions to any CIOs. That's for sure. They've got a tough job. They don't last long. That's the problem. Okay. So laptop A has something to send to B. He thinks he knows how to get there. He has an entry in his routing table, so he sends it to R1, and R1 realizes he is not the right person to do it. But in his routing table, he knows who is, and it's someone else on the same LAN that is on the LAN with us. It's R2. So he will send it to R2 because that's what routers do. They route, and R2 will send it on its journey towards B, but he will also send a redirect message to A to tell him, please update your table. Please correct your route. So for this reason, a host usually starts with a small table and accumulates routes as time goes on. and a redirect message is one of the way you accumulate routes. You can see them in trace routes. And I don't know if we can find it, but let me see if we can find one. Because you have a destination IP address and you don't know where to send it, so you just send it to the default gateway, but that's not the right one to send it to. The second router is there specifically to reach this network, and you just didn't know that yet. So you send it to where you send everything, but you don't know what to do with, to the default gateway. It sends it to the default route, or if it refuses, it will send you back a network unreachable ICMP error message and tell you it's not there. So let's see if we can find a TCP redirect, which I don't see in here. Dang it. All right, let's try this. God, am I still capturing packets or something? No, because this is like super freaking slow. All right, didn't like that. Let's take this off, go into just ICMP, and see if I can find a redirect message. MTU, that's one that's fun to look for. You can kind of see those in here as well. Why didn't it find anything in here? Reverse tunneling, UDP tunneling, redirection gateway. I don't know, that doesn't sound, that doesn't really sound all that convincing. But let's try it. Nothing. All right, so we don't have any in here that exemplify that. We can sometimes. All right, a couple of others in here. The message format, remember there's a type and then there's subcodes. You can have more than one code. They all have exactly the same type of structure. Echo request and echo reply. Anybody know what those really are? You have all run a program that uses echo request and echo reply. Do you know what it is? Want to see it? If I show it to you, you'll recognize it immediately. That's exactly what it is. So let's try doing that, and let's try ping rice.edu. Right, not getting any response. So what if I ping ITSMNX? Now I see requests and replies in different orders, right? So that's what's going on there. And if I do something like ping 5,000 bytes, then I get them back. But what I'm going to see here, if I look at one of the replies and scroll down here, it did not decode it, which is kind of interesting. So this is a fragment. That's what I'm trying to show you, is that this one is a fragment, but it didn't. Let me look at the rest of the replies and see if I can find another one here. Timestamp. Didn't give me the IP header. Wireshark may not decode these. Or there may be something I don't know about this option in my version of ping. Yeah, I saw this yesterday, the day before though, in class. So I don't know what's different about these. I don't know. No telling. Maybe they're too small or too big. I can try doing it again with a different size. Let's try 8,000 bytes. All right, and then stop this and see if these look any different. Nope. And we'll do it again. with 10,000 bytes and see if we can break it. Message too long. Nothing growing in Marshark. Never made it out the door. So my ping stopped it. Okay, so played around with that a little bit. Okay, timestamp, we'll skip that one. It just adds times in as you go. You remember how to do checksum, but checksum's been a little while for most of you. So just to recap, you have a packet. No, can't do that one. Got to do that. All right. So I have a packet. It's 32 bits wide if I choose to force it into the data structure that we see for every single thing we've ever looked at in class. And what I'm going to do is leave the field alone where the checksum goes, which is basically this field right here. It's not really where it goes, but I'm just going to pretend. And then I'll continue on with the rest of this. When it's time to calculate the checksum, I have the packet ready to go. I'm ready to transmit it. The last thing I do is I add up all of these numbers and come up with a subtotal. I take any carryout that happened and add it back in, and I have a sum. I have a total. Of course, this is all zeros at first, so it's part of the sum, but it doesn't change the sum, because adding zeros doesn't do anything. And let's say it's 100110101, and what do I do to calculate the checksum? I use 1's complement mass, so I added the sum, but I just flipped the bits. Now I have a checksum, and this is the real sum here. The checksum goes into this packet, and it's transmitted. That's the purpose of inserting it in there, to send along with the packet something that will help you discover if it's been corrupted. How is it going to help me discover it's been corrupted? When I get to the other end, I do exactly the same thing. I add all of these numbers up, but there's a way of writing the formula for what I've just done by adding them all up again. If there's no corruption, this number should equal the sum that I had before, plus the one field I added after I calculated the sum, which was the checksum field. So this sum should match this sum, and this should match this. So what I'm doing now is adding these two things together. What do I get when I add these two things together? All ones. So if you are writing assembly code, is there a simple math command that you can perform to check if it's all ones or not? So I would use overflow. There's more than one. If you add a 1 to this as an integer, the only time you'll ever have an overflow is if it's all ones. But you can and or, there's inverts, there's things that you can do. But the reason why I ask you about it is this is a good example that you'll probably agree with, where it does pay to know what's going on below you, because the choice to calculate a checksum like this probably came from the person writing the driver, who has to deal with the hardware. And understanding what they're doing, you know, you could come up with some other crazy checksum scheme, but this one could be done fast enough for the very earliest computers that were super slow to still let the packets come in the door fast enough.
Like, if you just check like only 5 volts or something, or like any electricity, and then the checksum is wrong or something.
Yeah. Well, and we, there was a very famous paper at Stanford. Have I told you guys this story yet? So maybe 10 years ago now, and the Cisco engineer participated in it as well. They looked at the error correcting code for Ethernet, and it's known that it was extremely resilient. And what resilience means for an error correction or an error detecting code is it will never get fooled. It will never allow a frame to go past that it believes is uncorrupted, but that in fact is corrupted. So there are theoretically more than one combination of bits that result in the same CRC calculation. Just like you can see there's lots of combinations that would come up with the same sum. You could change all kinds of bits and still come up with the same sum. CRC, it's much harder to do, but there are more than one. So it's theoretically possible for you to corrupt an Ethernet frame so much that it still validates with the CRC that's there. And that happens 1 in 4 billion errors mathematically, which is more often than you think, but it's still a big number. Not 1 in 4 billion packets or frames, but 1 in 4 billion errors. You get fooled in 1 in 4 billion errors. So armed with that statistic, they looked at a network, collected a bunch of network data, and they said, let's see how often things are being retransmitted. And they excluded the retransmissions due to buffer overflow, because that's not fair. That has nothing to do with error correction. And so they were able to see, kind of correlate that, probably looked at the source quince messages and things like that. And what they found was that retransmissions weren't happening 1 in 4 billion, they were happening about 1 in 1,500. Orders of magnitude more. Long story short, we write crappy code, and we build bad power supplies, and we make memory that's not very stable. And all of those things conspired in all of these devices along the way to pass along corrupted packets. After it's already had the error check done and it goes into memory and it's corrupted, or power voltage flips bits, you know, it's all that stuff. Yes, sir.
So ECC memory actually helps a lot.
ECC memory is the memory that's causing the problem.
Really?
Well, I mean, the reason, the type of memory that we use in input ports on cards is a special type of memory that is unlike RAM that you normally use. It's supposed to be error correcting, and maybe now they actually have more. But what this memory does, and I'll think of the acronym for it again in just a second. But what this memory does is it has the ability to look in all memory locations simultaneously. So you feed the data bus. You don't do what you normally do in RAM, which is, with RAM, what you normally do is feed the address. Let's say it's a 32-bit architecture, and we can draw a much more complicated diagram, but for now, let's just assume it's all on one bundle of lines, and it points to a specific port of memory, and you have it dump its contents out. So when you and I write code to search for a number, we're dealing with this kind of RAM. So we have to go one by one by one to search. We may sort things ahead of time and do Newton's approximation to search, or have some other scheme, but we're limited by this type of RAM. Routers are not. Routers use RAM that can look in all sites simultaneously. So what routers do is they don't feed the address. Instead, they feed the data. And they ask all of these sites, every one of these locations, just like you would have somebody raise their hand if the address matched, you're going to have them raise their hand if the data matches. They're all having to look, and if the data matches, then they dump their address out for you here. So when a subnet mask is applied and you have the network number, you search through all million rows simultaneously with memory. And this is on every single card. This memory is on every line card. This is why routers are $100,000 and up. And there's other devices now in data centers that need the same type of memory that compete with us. And so that's been murderous. We've had shipment problems in the industry now for at least 6 or 7 years. And some of it began with the Fukushima disaster and the tidal wave in Japan, and wiped out a bunch of plants to do it. So we knew we were in trouble. We were in trouble then. We sent a boat out to look for chips that were floating in the ocean and snatch them up with a fishnet. I'm kidding. Okay, just want you to know. You don't know my sense of humor completely, but you should assume I'm kidding. Okay. All right, so that's the way that stuff works. So whatever they were doing wasn't working because we still had tons of errors. But that was a really interesting article, I thought. And I've tried getting a hold of the scientists at Cisco. They don't respond. They're probably overwhelmed and busy. But hey, so am I. You know. So same name on the paycheck. Okay, there's some other stuff in here that shows you how to do pings and trace routes, but we've done it. Last word on ping and trace route, they are application layer programs. ICMP is not. ICMP runs at layer 3. So ping and traceroute are two of the very few programs that you have where run as a regular user without super user privileges can cause a kernel call to get a ICMP packet sent out the door or some other type of packet sent out the door for you and the results to come back. So that's proven really, really helpful. They didn't intend for it to do that. Module, input, output, super simple. Output module gets stuff out the door. If you get a request from an application to send out a query, like ping, then you send it out. If you get a request from UDP or TCP to complain about a bad packet someone sent you, like they sent you a packet with a port for which there's no one listening, you don't know that until you get to the transport layer. So errors can originate from these guys. You also can have your own errors that are originated yourself. Like if things get to IP and there's a bad parameter, for example, or a time to live is expired. That's a problem that layer 3 will discover. So this is basically a walkthrough. So the input module, if the type is a request, then respond to it. If it defines a redirection, then update your routing table. If it's another type of error message, then hand it up and let the protocol know. Let UDP know, let TCP know, whoever the error is for. Let them know what's going on. The output module, if you get a demand, a request to build an error message, and it comes from IP, but it's not one that makes sense to send, then ignore it. If it is a valid redirection message that you're asked to send, then return. There's nothing you really, nothing more you really need to do. If it creates a request, then create it and send it. This one is more obtuse. I find ICMP harder to understand how I get my arms around writing the code than I do IP and TCP. As difficult as they seem, you remember when we walked through the IP code, it's like, that's it? Yeah. So of course there's more detail, but that's basically what's going on. Okay, believe it or not, guys, we're finished. There he is. You guys like, you don't know that joke? It's like one of the best jokes of all. When somebody walks into the room, you go, shh, there he is. Makes him super paranoid. The whole joke goes basically, shh, there he is. So then the queen said to the king, oh hi, Bob, hi. He like turn to them and act like, yeah. Okay, questions on this stuff? So we have a test in 2 weeks.
Yeah.
All right, yeah. Don't it'll be okay. Was the last one No, that's too late now. You don't need them anymore. It's not cumulative.
You're about to present the second one. Forget the first one.
Yes. Go with that. Forget it. Forget. All right.
Now, it's like,
There's always one. There's always one.
there are two.
Let it go. Let it go.
¿No quieres examen? Pues sí, ya se lo mandamos. Ah, ok, ¿ya lo olvidaste tú? Ok.
Oh, look at this. I got some destination unreachables on packet 105,891. Maybe I should stop capturing. No.
You're all ready to it.
Okay. That's it. We're done, guys. See you, Jesus. Bye. See you later. Yes. Say that again? Oh, really? I'll have to send them the... Well, somebody showed up. That's you. That's why.